Welcome to Episode 60, Reliability and Resilience at Scale. The fundamental principle of cloud engineering is simple but absolute: design for failure, always. Systems that assume perfection eventually collapse under pressure, but those built for failure adapt, recover, and improve. Reliability means delivering consistent service within defined expectations, while resilience is the ability to withstand and recover from disruption. These are not one-time achievements, but ongoing disciplines woven into architecture, operations, and culture. Google Cloud's global infrastructure enables high reliability, but true resilience depends on how customers design their systems, anticipating the unpredictable, planning for loss, and building confidence through continuous testing. At scale, resilience becomes less about avoiding failure and more about mastering it with preparation, automation, and learning. Service-level objectives, or SLOs, translate reliability into measurable goals. An SLO defines the acceptable level of performance, such as uptime, latency, or error rate, for a given service. From that target emerges an error budget, the permissible amount of failure within a defined period. For example, a 99.9% availability goal allows roughly 43 minutes of downtime per month. Error budgets balance innovation and stability. Teams can deploy new features until the budget is consumed, then focus on reliability until it resets. This data-driven balance turns reliability from intuition into management science. It ensures that decisions about change, release cadence, and risk tolerance remain grounded in quantifiable limits rather than guesswork. Multi-zone deployment should be the default stance for production workloads. Within each Google Cloud region, multiple zones provide physically separate data centers connected by high-speed, low-latency links. Deploying across zones protects against localized hardware or network failures while maintaining minimal latency for users. For instance, a web application hosted in two zones can automatically shift traffic if one becomes unavailable, continuing service uninterrupted. The cost of deploying multi-zone is far lower than the cost of a single outage. By assuming that any component can fail at any time, teams design redundancy as standard practice rather than exceptional precaution. Resilience begins with this foundational principle: distribute everything that matters. Regional failover and data replication extend reliability beyond single zones. Regions provide geographic separation, ensuring continuity even when an entire data center cluster or area experiences disruption. Data replication across regions can be synchronous for critical low-latency workloads or asynchronous for cost-sensitive ones. For example, a financial transaction system may use real-time replication between two regions to maintain consistency, while analytics workloads replicate more flexibly. Automated regional failover ensures that applications reroute seamlessly during outages. These designs trade some complexity for a dramatic gain in resilience, protecting users and organizations from events ranging from power failures to natural disasters. Geographic redundancy transforms isolated reliability into systemic resilience. Load balancing and health checks form the operational nervous system of distributed systems. Load balancers distribute incoming traffic across healthy instances, optimizing performance and minimizing overload. Health checks continuously probe applications, removing unhealthy nodes automatically until they recover. For example, an HTTP health check might send a simple request to confirm an application's readiness. When combined with autoscaling, load balancing ensures that systems respond to both failure and demand without manual intervention. It smooths out irregularities, absorbs spikes, and maintains user experience even when components fail silently. Properly tuned health checks turn detection into response, eliminating delays that could magnify disruption. Backoff, retries, timeouts, and idempotency are programming patterns that enable graceful recovery from transient errors. Exponential backoff delays repeated requests after failure, reducing strain on recovering services. Timeouts prevent operations from hanging indefinitely, ensuring resources remain available. Idempotency means that retrying an operation produces the same result without duplication, a key principle for tasks like billing or message delivery. For instance, if a payment API call fails midstream, an idempotent design guarantees that retried requests do not double-charge users. Together, these patterns create stability through discipline. They prevent cascading failures, reduce congestion, and make systems predictable even when networks falter. Reliability grows from small, consistent design choices embedded in every component. Stateful patterns such as quorum and consensus maintain integrity for systems that rely on shared data. In distributed environments, multiple nodes must agree on the current state to avoid conflict. Quorum ensures that a majority of nodes participate in each decision, while consensus algorithms like Paxos or Raft coordinate updates across replicas. For example, a replicated database may require agreement from at least 2 of 3 nodes before committing a transaction. These patterns tolerate partial failure while preserving correctness. They make data reliable even when hardware, networks, or processes behave unpredictably. Designing with quorum and consensus principles prevents split-brain conditions and ensures that critical information remains authoritative and recoverable. Chaos testing and game days transform resilience from theory into measurable practice. Rather than waiting for failure, teams deliberately introduce it under controlled conditions to observe system behavior. Chaos testing might disable servers, degrade networks, or simulate regional outages. Game days expand this concept into collaborative exercises where operations, development, and business teams respond to realistic incident scenarios. For example, simulating a database outage during peak hours tests both technical and procedural readiness. The goal is not to cause disruption, but to build confidence through rehearsal. Each exercise exposes weak points, validates monitoring, and strengthens response muscle memory. In the cloud, practiced chaos becomes the foundation of call recovery. Capacity planning and surge controls maintain performance during fluctuating demand. Predicting required capacity involves analyzing historical data, identifying peak usage patterns, and maintaining buffers for unexpected surges. Autoscaling automates this by adjusting resource allocation dynamically, but it must operate within predefined limits to prevent cost overruns or unstable growth. Surge controls like request queues and rate limits keep systems responsive under stress by prioritizing essential traffic. For instance, during a retail sale event, non-critical background tasks might pause to preserve bandwidth for customer transactions. Thoughtful capacity management ensures that reliability does not depend on infinite scaling, but on planned elasticity and measured restraint. Dependency mapping and blast radius analysis identify how failures spread through interconnected systems. Every service depends on others. Databases, authentication, APIs, and a disruption in one can cascade to many. Mapping these dependencies visually clarifies where to invest in redundancy or isolation. Reducing blast radius means designing components so that failure in one area does not impact the whole. For example, partitioning services by function or region limits collateral damage from localized outages. Dependency awareness shifts the mindset from what failed to what else could fail because of it. By visualizing relationships, teams gain foresight, minimizing surprise, and maximizing containment during real incidents. Backup, restore, and runbook drills transform theoretical recovery plans into practiced reality. Backups preserve data, but restoration procedures confirm their usefulness. Automated and versioned backups reduce human error, while periodic drills verify that recovery time objectives can be met. Runbooks document detailed step-by-step instructions for restoring systems under pressure. For example, restoring a production database from snapshot should be a rehearsed, predictable process, not an improvisation. Regular practice ensures that no one has to learn recovery procedures during a crisis. True reliability includes not just keeping data safe, but ensuring it can return swiftly and completely when needed most. Telemetry captures the pulse of reliability through golden signals and saturation tracking. The 4 golden signals, latency, traffic, errors, and saturation, offer a concise view of system health. Latency measures responsiveness. Traffic indicates load. Errors reveal failure rates, and saturation shows resource limits approaching. Observing these metrics continuously allows early detection of performance degradation. For instance, increasing latency paired with rising saturation often signals impending overload. Dashboards and alerts convert telemetry into operational awareness, guiding both immediate responses and long-term improvements. Measuring reliability makes it visible, actionable, and steadily improvable through feedback and iteration. Post-incident reviews and learning loops close the resilience cycle by transforming failure into insight. After each incident, teams conduct structured reviews that analyze causes, responses, and outcomes. The goal is not blame, but learning, identifying systemic weaknesses and updating processes or tools to prevent recurrence. A good review produces follow-up actions that enhance automation, monitoring, or design. For example, discovering that alerts were too noisy might lead to revised thresholds or event correlation improvements. Continuous learning turns setbacks into progress. Over time, each incident becomes an investment in reliability maturity, reinforcing resilience as an evolving, collective discipline rather than a static goal. Resilience is a continuous practice, not a milestone. Every deployment, configuration, and review either strengthens or weakens it. In the cloud, where systems are vast and dynamic, reliability emerges from culture as much as code. Designing for failure, measuring performance, and learning from disruption form an ongoing loop of improvement. Automation handles scale, but human curiosity and discipline sustain it. When organizations embrace resilience as a habit testing, assumptions, refining processes, and sharing knowledge, they move from hoping for uptime to engineering it deliberately. Reliability at scale is not perfection, but preparation, ensuring that no failure becomes final and every recovery makes the system stronger. Thanks for listening. For more audio courses, daily newsletters, and more, please visit DailyCyber.News.